The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and welcome to this live learning event entitled Interactive Conversation on Controlling Groundwater in Mines, Tunnels, and Subways. My name is Don Rigby, Director of Marketing for Avanti International, and today I get to introduce you to some pretty savvy people and facilitate a session to maximize the next 59 minutes for you. And based on scientific data, cementitious and solution grouting is a proven, cost-effective answer for controlling groundwater. And for groundwater operations, these tactics will maximize production in new construction and provide long-term benefit for maintenance and rehab operations. Each are engineered and produced with unique properties to provide specific performance attributes. You'll learn directly from our panel of experts today who have devoted their professional lives to this industry and enjoy teaching what they know so others can do. The platform we're using has all participants on mute, but it's important that we get interactive, and here's 3 ways we'll get that done. Yesterday I sent an email inquiry asking, what's on your mind? And requested a reply so that we can be relevant to your information needs. We received good response from this, from name brand companies all the way from Canada to Colombia, South America, and all points in between. So this is one way we keep this an interactive conversation. The second way is answering your online questions. And we reserve the last 10 minutes for Q&A, but I recommend as questions come to mind, immediately type them into the collapsible dialog box to the right of your screen. As appropriate, I'll interrupt the speaker or choose to reserve it for the end. But if we don't get to all the questions on this webcast, we'll answer every question individually by email, and that's a promise. The third interactive mechanism are poll questions. And these are very interesting because I play back the answers right away, and you can see how your opinions stack up with your contemporaries. In many ways, these questions lead the presentation. So let's begin the first one right now. I'm going to multitask and launch this first poll question. What are the risks associated with uncontrolled groundwater? Folks, there's no wrong answer here. I'll let you review each response. And but in your opinion, what's the single best answer? Answers are pretty pouring in, pretty dynamic group here. There is no test at the end. All right, I'm going to close out this poll question, and then I'll play back the responses. Higher cost of maintenance and rehabilitation. Worker, public safety. Very good. Subject matter experts, please take note, and to the degree we can tailor our presentation to this, that would be a good thing. I'm going to hide this. And I would love to introduce our experts for today. Thank you for submitting that response. Look, Ward Knotts is President of ECO Grouting Specialists, a design and consulting organization established in 1982. Without question, a true innovator in the grouting industry with a world-class testing facility that back up everything he says, everything he does. Ward, thanks for being here today.
Thanks for having me. Good afternoon, everybody.
Brian Jepson is Vice President of Research and Development at Hess Pumice Products in Idaho. And U.S. Grout is one of their mined and manufactured products. Brian's responsible for testing ultrafine and microfine cement grout in unique and challenging environments. Brian, again, thank you for being here.
It's my pleasure to be here. Well, welcome, everyone.
And Britt Babcock is an engineer and heads up the geotechnical division for Avanti International. He's a road warrior, so to speak, investing half his time on job sites with contractors and the other half with the engineering community on job specifications for both chemical and cementitious grout. Britt, are you ready for this presentation?
I am. Thank you for having me.
And to start us off, I'd like for Britt to begin the first segment on one of Mother Nature's manufactured products, and that's groundwater. And Britt, I will make you presenter. I'll let you acknowledge and take off.
Thank you, John. As everybody knows, groundwater, or more importantly, groundwater infiltration can be very relentless. When the chances of water infiltrating any project, and this is very high, especially since there's given so much water on the planet, over 326 million trillion gallons. And some of the things that we face day to day are sort of reflected in that last poll question. Safety is definitely one of the top most important things on any job site, with one of the biggest threats is immediate flooding. That can cause a lot of problems. Many times most designers will try to foresee this with pre-grouting programs for the subsurface soils or rock to achieve safe and manageable inflows, but those unforeseen can definitely cause immediate flooding and even loss of ground. Next issue is environmental, contaminated water or water tables. A lot of regulatory agencies require treatment of that groundwater prior to us recharging that back into a water or a stream, or even back into the groundwater table. And obviously, the fewer the number of gallons that are pumped out of the ground, fewer gallons that are treated for fewer dollars overall. Next are costs associated with pumping in itself and or reduced or stopped production or operational interruptions. If unforeseen, those types of water inflows, which can happen, can cause shutdown of a project and very costly remediation plans to get back up to speed. I mean, time is money on a construction site. Some of the challenges alone can be exacerbated by water with either the advancement of a mine slope or a mine shaft, or the advancement of a TBM. Can be greatly exacerbated and challenged by the presence of water. And then, of course, the operating and maintenance nuances that come into play with the introduction of groundwater, the incessant or onslaught of groundwater over time can cause equipment issues, corrosion on tracks or associated components, things like that. Can also create worker and public safety issues with trip and slip hazards. So really, in summary, to recap and essentially that poll question, and I think a lot of people touched on that, groundwater can be very challenging and causing big difficulties with design, construction, and maintenance. And for contractors, engineers, and owners and or agencies to have to deal with on a day-to-day basis with any underground construction project, these issues can be very costly. And I think everybody is well aware of that, since there's millions of dollars spent annually to try to remediate and control the inflow of groundwater in underground constructions. But through the assistance of designers like Ward Knotts, who we have on the phone, the webinar today, with ECO Grouting Specialists and the use of cementitious grouts or chemical grouts and solution type grouts, these challenges can be handled. They can be managed down to acceptable levels, and in some cases even eliminated. I'll pass it on now to Ward. Ward, I look forward to your grouting design presentation.
Thanks, Britt. Grouting is nothing but a continuous and prolonged hydraulic conductivity test using grout as a test fluid. As is done during a hydraulic conductivity test to determine the permeability of the formation, the injection rate and pressure is recorded during the actual grouting operation. This information allows practitioners to approximate the average permeability value of the formation as the grouting operation progresses. Since the goal in most grouting applications, as Britt alluded, is to reduce the permeability of soils, rock, or civil structures to meet a certain permeability target. Monitoring the evolution of this permeability value as the grouting operation progresses provides an effective and simple way to evaluate the effectiveness of the grouting operation. This particular borehole that you see on the slide produced significant quantities of water under high pressure. But a key component to any grouting operation is, of course, the grout. The selection of what type of grout, or grout for that matter, to inject can be very difficult. There is no such thing as a wonder grout. That is why oftentimes a variety of grouts is required to achieve certain residual permeabilities. However, by selecting the appropriate grout, the effectiveness of grouting operations can be maximized. These are examples of large dam and shaft projects where in situ hydraulic conductivity tests or water tests were conducted prior to designing the grouting program. The water test in the brush on the previous slide eventually resulted into this rather large shaft. And here's where the amenability theory comes into play. The amenability is a measure of the suitability for a given suspension grout to permeate fissures and apertures accessible to water in the grout zone. The amenability coefficient of a formation refers to what percentage of pores and fissures that are accessible by water that are also accessible by grout. So it's a quick and scientific method to determine if a grouting operation is on the right course or changes are required. Prior to injecting the grout, the permeability or Lujon value of a formation to be grouted can be calculated by conducting what is commonly referred to as a water test or in situ hydraulic conductivity test. And just to clarify, 1 Lujon is approximately 1 × 10⁻⁵ centimeters per second. Water is used as a test fluid and injected in the zones that are targeted for treatment. The total aperture size intersecting the borehole accessible to water is calculated. During the initial stages of grouting, the Lujon value for the same formation is determined, but this time with grout as a test fluid, often referred to as Lu-grout. And it's the ratio of the Lujon values, the Lujon value of the grout divided by the Lujon value of the water, that is referred to as the amenability coefficient. And the ratio or amenability coefficient effectively sets the limit of what type of reduction in permeability can be obtained using a particular type of grout in a formation. And this slide here shows a real-time monitoring system that conducts all the calculations in real time. The amenability coefficient will immediately signal if the selected formulation is suitable, somewhat suitable, or not suitable at all. The amenability coefficient indicates where or if regular cement-based grout is no longer suitable and one has to resort to a formulation with finer particles or a solution grout that does not contain particles. And solution grout is just another term for what some people refer to as chemical grout. In a limestone mine in Missouri, the construction of 2 sloped tunnels was temporarily halted due to significant inflows. The grouting operation was reviewed and the amenability theory was put to work. Despite very high inflows, the amenability coefficient of the formation using regular cement-based suspension grout ranged from 0.01 to 0.05. This meant that only 1% to 5% of the pores accessible to water are also accessible to regular cement-based suspension grout. The amenability coefficient of microfine cement was approximately 16%. This indicated that in this particular formation, conducting cement-based suspension grout operations would be a waste of time, as at best the residual permeability would still be 84% or higher. Although it seems counterintuitive because of the large inflows, cement grout would be of very limited use. Once the grouting program was switched to a predominantly solution-based grout, the inflows were brought under control. And this is again the first slide, which is a picture of a grout hole in a mine. The outflow here was up to 600 liters per minute, which is about 160 gallons per minute, at a pressure of up to 900 psi. The amenability coefficient for cement-based grout was pretty much 0, which means this formation will not accept a drop of cement-based suspension grout. In a recent project, a TBM was launched from the bottom of a 93 feet deep starter shaft on Fisher Island, approximately 20 meters from the Atlantic Ocean, so no shortage of water. Once the TBM broke through the secant pile wall, enough water came through and around the portal to flood the shaft and the TBM. A grouting program was designed with regular-based cement, and even though the grout hole spacing was extremely tight, the grout bed was very poor and the residual permeability remained high. The amenability coefficient was quickly calculated, and it became clear that microfine cement-based grout was required. The microfine cement-based grouting program reduced the permeability considerably, but the amenability coefficients indicated that the residual permeability and subsequent inflow would still be too high. The residual permeability was further reduced with solution grouts. Grouts again with no particles. This slide is a view of the grouted formation once the TBM was removed for repairs. All the various grouts are visible, and you may notice that there are two different colors for microfine cement, as two different types of microfine cement were used. The dark green or blue would be a slag-based microfine grout, and the lighter colored grout would be a pumice-based microfine grout. And with this, I'm going to pass it to Brian.
Thank you very much, Ward. Appreciate your presentation there. It's great to have you with us today, and we certainly appreciate your contribution to this broadcast. I've been asked to cover some of the most common tests that can be performed, both in the field and in the lab, that will help ensure a quality grout solution. Today I'll be focusing on those tests that are geared towards cementitious grouting, which we perform here on a continuous basis in our efforts to improve our grout performance in a variety of applications. Recently, I was privileged to see the value of these performance tests firsthand as I visited Ward and Eric and their team at ECO Grouting. Interestingly enough, there are very few tests that have been designed specifically for the grouting industry. In fact, most of the tests that are used today were originally designed for the drilling industry. Of course, the first step in evaluating a grout formulation is to correctly mix up the solution. In the lab, as well as in the field, when using an ultrafine or microfine cementitious grout, it is very important to use a high-shear mixer. This shearing action helps to facilitate the complete wetting and dispersion of each solid particle in the grout mix. Without this shearing action, it is likely the grout solution will contain agglomerated grout clumps that will impede the grout's performance. After mixing, dependent upon the particle size of your grout, one of the first tests performed will be either the flow cone or the Marsh funnel test. Both tests are used to evaluate the flow properties of a solution and measure the efflux time, or the time required in seconds for a given amount of solution to flow through the cone. The flow cone test is effective in measuring neat OPC grout solutions, as well as grouts containing aggregates up to a maximum particle size of 2.36 millimeters, or just under 1/10 of an inch. The Marsh funnel test, which is very similar in method and reporting to the flow cone test, is better suited for the finer particles found in today's microfine and ultrafine grouts. The baroid mud balance is a simple device used to determine the specific gravity of a mud or grout solution. This test is extremely valuable in the lab to determine the stability of a grout when used to measure both the pre-injected grout solution as well as the reclaimed post-injected grout. In the field, it is very useful for monitoring the consistency of a grout formulation prior to injection. Bleed in a grout solution is caused when the solids in the grout separate from the liquids. This can be very problematic, especially with higher water-cement ratios. Being able to evaluate the bleed of a grout formulation in the lab is very important when designing stable grout mixes. Essentially, this test is performed by pouring the freshly mixed grout solution into a 250 milliliter graduated cylinder and then measuring the amount of separated bleed water at 2 and 24 hours. The results are reported as a percentile. With regards to bleed, a grout is considered stable when it has less than 5%. However, the ideal would be less than 2%. Two important factors that help identify the workability of a grout formulation are the gelation and the set times of the grout. This hand vane tester on the left is one way to measure the initial and final gelation times of a grout. This helps to establish the window of pumpability of the grout solution. For example, if a grout has an undisturbed initial gelation time of 2 hours, then the contractor could be relatively safe in pumping up to that length of time, especially if he has kept the grout in agitation during the process. The Vicat needle on the right is used to measure the initial and final set times, which indicate the various stages of curing of the grout. Being able to quantify the cohesion, the plastic viscosity, and the yield point values of a grout can also be very valuable in determining how it will perform in the field. This is a fairly simple lab test where the mixed grout is tested using a viscometer, much like the one shown here. The pressure filtration test is another important lab test used in determining the stability of a grout. Although similar to the bleed test, the pressure filtration measures the separation of water from the grout solution under pressure. In most grouting jobs, strength is of little concern as long as it is at least as great as that of the soil or rock being treated. Since most grouts do not contain aggregate of any appreciable size, test specimens are usually cast in either the 2x4 cylinders or 2-inch cubes. Two variations in measuring compressive strength in grout are to measure either in the pure or neat condition or as a grout solution injected into a soil environment. In conclusion, I love this quote by Admiral Harper: "One accurate measurement is worth 1,000 expert opinions." However, with that said, as valuable as these test results are, it is the correct interpretation of the results that truly benefits any grouting project. This is the real value of contracting out the services of a reputable grout consulting company like ECO Grouting. With that, I'm going to turn some time back over to Don.
Yeah, that was well said, Brian. If you'll advance the slide one more time. But before I go into another interactive poll, I do want to address a couple questions and a request from Brad Crenshaw. Brad, thanks for being on this call and this webinar. The white paper requests that you indicated, I will certainly share that information at the end of the presentation. It'll be sent to you within 24 hours of this event, all three of them. But here's a question that deserves some immediacy, and I think that this is squarely a question that deserves Ward's response. Based on the amenability coefficient, when do you switch to microfine grout?
Okay, well, that's a good question. When the amenability coefficient is very low, let's say 0 to 50%, there is not that much merit in using regular cement because the cost of the crew and equipment and the cost of drilling holes will likely outweigh the benefit of the result that can be obtained with the grouting operation. In soil grouting, a grouting pass can be attempted, a first grouting pass can be attempted in the sleeve pipe with regular cement, and then the sleeve pipe can be regrouted with microfine cement or even a solution grout. So there's a bit of a difference there. In rock, the rock grouting, that is, the economics of drilling holes comes into play, as a grout hole can typically be injected only one time. So it becomes a technical and financial call. And I suppose the scope of the grouting operation also plays a role. But in general, with a low amenability coefficient in rock, I would switch to a finer grout almost immediately. Hope that answered it somewhat.
It does. And economics are always an issue here, Ward, so thanks for responding. I'm going to go ahead and launch another poll question, and I'll ask for each of your contributions, if you don't mind. What grout performance attributes are most important to you? Now, to answer that effectively, you probably have to think about a current project or an imminent project coming up. If you would respond to which one of those attributes are most important to you. This is not a trick question again. And we're about 50% voted. I'm going to give it another 10 seconds. About 80% voted. All right, I'm going to close this and then share it. I'm not sure there's any surprises there, but it does help us in the next presentation going forward, and I will ask that that Brian continue on and talk about the next slide, the next presentation on performance attributes.
Okay, thank you, Don. Just to kind of segue into the performance attributes of grout, here we have a good visual of a standard sand column test used to demonstrate grout penetration in a soil stabilization application. On the left, we have a sand column that has been injected with standard OPC grout. This is compared to the ultrafine cementitious grout on the right. As you can see, in this case, the soil conditions required a finer particle size in order to successfully permeate this sand column. As we see here, the ultrafine particle on average is 5 times smaller than standard OPC grout particle, and therefore is better able to penetrate these smaller voids. Here we see an example of how these ultrafine grouts can also be used to successfully penetrate microfractures. This is a cutaway sample of a successfully grouted salt cavern structure that shows by the black lines here that these tiny cracks have been filled by pressurizing the grout into the cavern walls. Some of these finer lines are the size of about 6 microns. This is an actual X-ray photo of ultrafine cementitious grout flowing through a 7.9 micron opening right there. To put this in perspective, the average human hair has a diameter of right around 80 microns. So the constriction you see in this photo is approximately 10 times smaller than the average human hair. Right there. Wow. Another factor in the ability of a grout to effectively penetrate, whether the application is geotechnical or structural, has to do with viscosity and flowability. Contrary to general public's understanding, the two are not always synonymous. A liquid's ability to flow does not always correlate with its viscosity. Viscosity can be defined as a liquid's thickness, which does not always correlate with a liquid's ability to flow. Rheology is the study of the flow of matter. And although there is most certainly a relationship between viscosity and flow, they are not always exactly the same. Here's a simple example that we did here not too long ago. Here we took an ordinary glass of tap water, ran it through the standard marsh funnel test. The resulting time was 28 seconds. We then added a common household rinsing agent, effectively reducing the surface tension of the water, and reran the test. This same amount of fluid ran through the funnel in 26.5 seconds. Although the viscosity remained exactly the same, the water's ability to flow was increased by 5%. This becomes a key factor in grouting applications and emphasizes the importance of selecting the correct admixtures for your specific project. Let's talk for a minute now about grout composition. Although there are various types of cementitious grouts, most consist of a mixture of a Portland or other type of cement and other various types of supplemental cementitious materials known as pozzolans. Well, what is a pozzolan? The value of having a pozzolan in a cementitious grout is significant. The long-term strength and durability of any cementitious product is derived from the calcium silicate hydrate that is formed as a reaction between Portland cement and water. The more cement that you can get to convert to CSH, the stronger and more durable your cementitious product will be. Without pozzolan, only about 75% of the Portland cement makes this conversion. The remainder is converted to calcium hydroxide, which does not add to the strength, but can actually be detrimental to the final product. Pozzolans in and of themselves are not cementitious. However, because of their high amorphous silica content, when they are finely ground and added to cement and water, they produce an important chemical reaction which converts the leftover calcium hydroxide to the desired CSH, thereby strengthening the cement and reducing the negative effects of the calcium hydroxide. This CSH conversion process can continue for decades. As Ward mentioned earlier, excuse me, when the amenable coefficient indicates that cementitious grouts are unable to penetrate the geology, the use of a solution grout is warranted. Solution grouts are typically very low viscosity, two-component grouts consisting of acrylamides, acrylates, or sodium silicates. Solution grouts are used generally to permeate soils or penetrate intermatrix geologic formations to control groundwater or stabilize soils. Acrylamides and acrylates are generally used for more permanent water control, whereas they have lifespans of 360 plus years and 50 years respectively, while sodium silicates are considered for temporary water control and soil stabilization with a functional lifespan of only a few years. With regards to viscosity, acrylamides are in the range of 1 to 2 centipoise, while acrylates are slightly thicker at 3 to 4 centipoise, and sodium silicates typically range in the 6 to 7 centipoise. Most acrylates and sodium silicates have set times that range from a few seconds upwards to an hour. In contrast, Avanti's acrylamide and acrylate grouts have the ability to control set times from a few seconds to nearly 10 hours. That brings us to the end of my portion of the presentation. I'll be glad to turn the time back over to Ward to discuss a few injection techniques.
Thanks, Brian. I'm going to spend a couple minutes on the difference between soil grouting versus rock grouting. Soil grouting and rock grouting both have the word grouting in their title, but this is where a lot of the similarities end. This slide shows grout holes in a rock face in a limestone mine. Typically, in rock grouting, a borehole is drilled to a certain elevation or location, and in a good percentage of the cases, the rock is of sufficient quality that the borehole remains open. Sometimes the borehole is subjected to a variety of borehole preparation procedures to clean the borehole from debris and to ensure intersected fissures and pores are accessible to grout. The borehole may receive an in situ hydraulic conductivity test or water test and is subsequently grouted. Typically, this is the end of the history of that particular borehole. Indeed, sometimes the borehole is partially re-drilled to a deeper elevation and regrouted, but typically a borehole in rock grouting receives one grouting pass. In soil grouting, a borehole is drilled to depth and equipped with a sleeve pipe, also known as tuba manchet and also known as a TAM pipe, and there might be other names for it too. This slide features a sleeve pipe which is being tested with water. On the enlarged section, you can see water exiting the pipe via the sleeves. This grout delivery system was invented by the French in the 50s and has essentially remained the same. It's a pipe equipped with ports, which are typically small holes or slits that are covered with sleeves. The sleeves are made of rubber and act as one-way valves. The ports are spaced at regular intervals, and the grout is delivered in the pipe via a single or double packer. The sleeve pipe allows practitioners to inject the grout at specific locations in the subsurface, and the pipe is re-injectable. The re-injectable feature is the key component to any soil permeation grouting program. This slide features steel sleeve pipes that were installed horizontally. The previous slide featured PVC sleeve pipes. The key to success in virtually any soil grouting is that the strata targeted for treatment needs to be injected multiple times. The formation in this slide was subjected to several grouting passes to facilitate the construction of a tunnel. The tunnel trajectory traversed through rock for the entire section, with the notable exception of this section in the slide. The rock dipped and was absent, so the soils through which the TBM had to mine were grouted and consolidated prior to any tunneling operation. So it's a kind of pre-excavation grouting program. Initially, the zones that are the most pervious during the first grouting pass will be the least pervious during the subsequent grouting passes. And by injecting soils multiple times, solid grout columns can be created. And when the columns overlap one another, a grouted conglomerate can be created. In addition to different grouting delivery mechanisms in rock versus soil grouting, the grout formulations may also differ in rheology. And naturally, refusal criteria for an injection of grouting paths in rock will differ from a grouting path in soil. In rock, it's typically recommended to grout to absolute refusal and sometimes maintain pressure on the grout hole for a certain period of time or until grout has reached a certain stage of gelation. In soil grouting, often there is a volume refusal criteria for a particular grouting path. And these are just some of the many differences between rock grouting and soil grouting. And with this, I'm going to pass it back to Britt.
Britt, you could be on mute.
Thank you, Ward. I'd like to dive into now some case studies where both microfine cements or ultrafine cements and solution grouts in mining, tunneling, and subway type applications. To begin, a couple of notable projects where cements were used, or ultrafine cements, Notre Dame Stadium and Rose Bowl. These were stabilized. Tunnels accesses into both of these structures were stabilized using cementitious grouts. So good successful projects in that application into soils and rock. Next project is a WIP, or the Waste Isolation Pilot Program, where cementitious grouts are used to seal water inflows for the disposal and storage of hazardous waste at depth within sedimentary bedrock type formations. Next project is Hollywood Tunnel out in LA. Cementitious grouts were used here to help re-level this in order to reestablish the tunnel alignment. Another project, this is a project that Ward has already alluded to, limestone project where water infiltration was a challenge. And of course they used a solution grout in this situation to help advance this mine slope because of the poor amenability of both Portland and a microfine cement in that scenario. Next project is Lake Mead. This is one of the intakes where cementitious grouts or ultrafine cements were used to seal high pressure waters into the rock fractures, to seal those off into the inflow into the intake tunnel. Very high pressures in that situation, and they were very successful in achieving a high reduction in water inflows. Another project, salt mine. As everybody knows, salts are highly dissolvable by water and can be very dangerous. Water inflows into these situations can quickly and rapidly flood the mine or cause dissolution of the salt itself. And so cementitious grouts used in salt mine type applications pretty extensively in order to help control water in that situation. Tunnel boring machine project in Houston. In this particular situation, what they had was they anticipated homogeneous material throughout the entire TBM alignment, but what they encountered was a softer zone above as the TBM progressed, causing the TBM to pitch up. They actually came in and reinforced or chemically grouted that weaker zone, allowing the TBM to have enough resistance and maintain alignment on that particular project. So that project did finish successfully, and it was a sanitary sewer force main, or gravity main. Another project that is not necessarily a shaft for a mine or a TBM, but very similar to a shaft type construction. This particular sanitary sewer overflow is 150 feet deep by roughly 150 feet in diameter. Here, both cementitious grouts and a solution grout were used to seal off water inflows that would have not allowed this construction to occur had the water not been controlled prior to the start of construction. Here you can see some of the leftover standpipes that were part of the construction that circled around the shaft, if you will. Coal mine in Illinois. Again, another project where both cementitious grouts and a solution grout were used in sedimentary bedrock type formations. They were able to pump both grouts over long distances and use the cementitious grouts into the fractures of the bedrock, and then use the solution grout in the matrix type geology that occurred within those mine slope advancements. Another project that's very notable is the Toronto TTC, or Toronto Transit Commission. They've been pumping a solution grout, encapsulating their subway systems and controlling groundwater for over 15 years successfully, and they've actually have their own internal team that has been doing that for 15 or 16 years now, and it's still ongoing. Many miles of existing subway with many more miles being installed, and the need for water control in that situation. Very successful. Don, I'll pass it on to you now.
And I'll take that pass. Thank you. And thanks to all the presenters for keeping us online and with the time, because I am adamant about starting this thing on time and ending it on time. And a couple things. Before we open up the Q&A session, and if you haven't submitted your questions yet, now's an excellent time to do so. But permit me to highlight something Avanti deems important. In the announcements leading up to this event, we itemized 5 takeaways that you would yield from this presentation, and above all else, we need to make certain we deliver on this promise. We learned how grout additives and admixtures enhance performance. From Brian, we learned why default into Portland cement may be short-sighted. And we now understand which QC test assists in making field adjustments. Ward showed us technologies and techniques for proper conveyance and injection, and we discussed why pre-planning and grout design are critical first steps, a core value of ECO Grout Specialists. I'd like to open this thing up now to a question and answer, and I have a plethora of questions, a few of which are very interesting here. What rule of thumb do you use for penetration of fractures? I have always heard that a fracture must be 6 times the size of the largest grout particle. Does that theory hold up to your beliefs? Let's say, Ward, I'll let you respond to that.
I think obviously you can't force a ping pong ball through the eye of the needle, but I think essentially the fracture, if the fracture is smaller than the particle size of the grout, it's not going to go through, but I don't think it needs to be 6 times larger, as long as for solution grout there are no particles, so they will go through it. And for particles, I think typically we look at the D90 and the D10 of it for it to go through. But yeah, if the particle size in the grout is larger, it will definitely not go through any pore or fissure, but I don't think it needs to be 6 times.
I like the analogy. Brian, you mentioned the sand column test. What is the real significance of this test in regards to real-world application?
Well, it's kind of in a real-world application, it's really kind of a partial test. Although it does demonstrate the permeability of a grout, to really have good application in the real world, you need to also capture the grout that flows through the sand. So that would be on the top side. Since you're injecting on the bottom, you would recapture that grout, do another mud balance test, and then compare the specific gravity of the grout coming out to the specific gravity of that going in, and that would tell you how many solids you lost, and probably an acceptable amount of solids to be lost would be, probably 10% or less. That would be your ideal.
I have a question or a statement from Adam, and this is not so much a question, but something that was missed potentially. While selection of an appropriate grout is important, the understanding of the geological,
Geology.
Thank you. Also dictates the success or failure of your grouting program. Britt, I know you wouldn't disagree with that at all. That's more of a statement than it is a question. Would you add color to that?
Yeah, I think Adams, and I think Ward would also agree to that Adam's absolutely right, that the geology that's intended to be grouted definitely plays a key role in having an understanding of that geology, whether it's a rock or if it's a sand, gravel, how much silts and fines are in that gravel. Potentially geology chemistry can play a role. Are you looking at brackish waters, are you looking at brine waters, or is it just a naturally occurring water that you may be encountering or trying to resist to keep from coming in? Geology is such a broad, encompassing topic and something we all walk on every day. Obviously, planet Earth is nothing but geology, and whether you're in Florida and the limestones there, or you could be in Tennessee and those types of karst formations, or you could be in the Rockies pumping into hard rock mines, or in Elko, Nevada. I mean, it varies versus the shore sands in San Francisco. All those different geologies play a key role in how to inject into those different geologies. So Adam's absolutely right. I agree 100% with that statement.
And I would agree too with that. I mean, it depends on whether there are flow conditions. Typically, you look at the geology before you start a grouting program, and it's based on boreholes, and geology is variable. So you might have two boreholes and correlate strata and anomalies, but there might be anomalies in between. So that's why you always continuously adjust your grouting operation in real time, because you need to respond to the geology. That is, if you're grouting a formation. If you're grouting a historical structure, it's slightly different, but even in that, there's a great degree of variance. But yes, you study the geology before you design a grouting program, and then during the grouting program, you adjust to even meet that geology to an even greater degree.
And even with that study, there's still some surprises. I know we've been called in on numerous occasions on an emergency basis that run into a layer of groundwater that they just didn't see or expect. And this happens all the time. Would you agree with that, Britt?
Yep, absolutely. Yep, it does happen. That's part of that unforeseen that I discussed at the first part of the presentation.
Right.
It can happen.
Brad Crenshaw, thanks again for your multiple questions. Yours seem to be pretty interesting and well-suited to address. What is the maximum percentage of fines for permeation grouting with microfine in soils? I think I would default again to you, Ward.
In general, we say the fines, the more fines, obviously, the harder it is to get proper columns. But with solution grout, I think it's up to it depends a little bit sometimes, because there's a variance in there, but 12%.
Very good. Let's see. In the slide I think that Brian presented, we talked about the solution grouts being acrylamide, acrylate, and silicates. There's a cost differential for each of these, and that tends to be a driver, not the only driver, but tends to be a driver. Britt, could you share how we might frame the cost factors behind each one of those types of solution?
Sure. Yeah, I'd be happy to. So we have acrylamides, acrylates, and sodium silicates from a solution grout perspective. I think it's fairly well known across the industry that sodium silicates are, of those three, the least expensive and are probably used on a higher percentage basis for temporary support or temporary water control. I think that goes without saying that that does happen quite a fair bit, and we'll be the first to admit to that and acknowledge that that does happen. The next step from a pricing perspective would be acrylamide. We estimate, I guess, getting back to sodium silicates to be roughly, I think, $2 to $3 per mixed gallon, which would include like a hardener and the components that go into that. Acrylamide would be the next step up in cost, roughly $6 a mixed gallon. And then acrylates would be a step above that at roughly $7 to $8 a mixed gallons. Where we see sodium silicates used, obviously, again, that's the temporary situation, temporary soil support, temporary water control. Acrylamides get used longer-term situations where they want to see a long-term water resistance and encapsulation, if you will, like in mine shafts, mine tunnels, mine slopes. They're also using an acrylic type-based product like an acrylamide or an acrylate in vertical shafts, as well as in and around subway tunnels. So where you're looking for that long-term water encapsulation, not encapsulation of the water, I apologize, dewatering system, if you will, to create that impermeable barrier is where we see the acrylic type products use the acrylamides or the acrylates, with the acrylamides actually having quite a bit larger lifespan, if you will, than acrylates. Acrylamides have over 360 years for the US DOE, whereas the acrylates have roughly just over 50 years. And then the industry perspective on sodium silicates, because they are temporary, just a few years. And I know that that could be argued anywhere from 2 years to 10 years to 20 years, but all of the grouting people involved in the grouting industry that I've spoken to have all kind of convened on back on the few years, and so that's where I tend to hover with my answer on sodium silicates. So, but they do have their place, and they are used quite a bit. But so does acrylamides and acrylates.
There is a cost-value equation to factor in here. Good. Thank you, Britt. And Brian, what are some of the additives that would help improve the stability of a grout solution?
Well, again, reviewing that stability is determined by how much of the solids stay in suspension. And so a couple of the additives that are very effective there would be your biopolymers, your diatom gums, your whelan gums, your bentonite would help maintain that. Also, one of the factors could be that your water cement ratio may be causing too much bleed, so you could replace some of the water with a superplasticizer. All of those, in any combination or one, could help to make your grout more stable.
Okay. As I suspected, we now have probably more questions than we have time, so I'll remind you, if we didn't answer your question live, we'll answer it personally by email, and I trust you're okay with that. So let's segue to our last and final interactive poll question. I'll launch it right now. What other geotechnical grouting applications are of interest to you? This time, check all that apply. And this will be very helpful to ourselves internally and our subject matter experts going forward. We're about 20% voted. Thank you. $57. This is good participation, guys. Thanks for contributing online with us today. I'll go ahead and close this out, and I'll share the response back. soil stabilization, consolidation, pre-excavation grouting. I'm not sure that I see a surprise there. I think that's probably consistent with what we may have expected. I will, as we wrap up this presentation, let me remind you that within 24 hours, you'll receive 3 documents by email, including 2 white papers and 1 published article. And with these, we extend the learning beyond this webinar. We love teaching what we know and believe about cementitious and chemical grouting. The only thing we like better than webinars is teaching nose to nose, belly to belly. And there's a hands-on training opportunity at Avanti's headquarters near Houston, Texas on March 18 and 19. This is our urethane injection school, but we're adding a wealth of geotechnical classes and workshops. You're encouraged to go to AvantiGrout.com to view this and other educational opportunities. Avanti is not a sales organization or a service organization, helping you specify and buy through teaching and consulting. And speaking of that, for those of you requesting PDH credit for your participation today, please email your request to Jessica Williams at AvantiGrout.com. I'll let you take a moment to jot that down. Jessica.williams@AvantiGrout.com. She'll confirm your participation for the full hour and issue you a certificate for 1 credit hour. Presenters, care to make any parting comments? And Ward, I'll begin with you.
Sure. I'd like to thank everybody for taking time out of their busy schedules, and hope that it may have been of interest. And I appreciate your time, and thanks again for having me at this webinar.
And Brian.
Likewise, it's been a pleasure to be with you. Hopefully you've learned what you've come away from this with some greater knowledge on the grouting applications. And if we can be of any help, please feel free to contact us.
And finally, Britt.
Yeah, I would like to, essentially my sentiments resonate that of both Ward and Brian. I appreciate everyone's time out of their busy schedule and appreciate the opportunity to be a part of this webinar. And we look forward to having the opportunity to assist and help further the industry as a whole in any way we can.
And I'll suggest to all 3 of you, you guys have been a joy to work with in producing this, live learning event. And certainly grateful, look forward to doing this again. As you exit this webinar, you'll be asked a few questions, and if you feel you were well served over this last hour, let us know. We fully intend to be the best in the business at these live learning events, and your feedback will tell us how. For now, all presenters and myself say thank you very much, and until the next time, so long.